Good evening, friends, and welcome to this evening's public lecture. May I ask you all to please put your mobile phones on silent mode? I've tried to verify that in my case 2 times. I hope I've done it. So we are ready to start our evening's proceedings. Let me request Professor Ashok Sen and our director, Professor Jairam Chenglur, to please come to the stage. Thank you. So we are really looking forward to this evening's public talk by one of the world's leading theoretical physicists, Professor Sen. And I will be introducing him in a more formal way shortly. But before I do that, let me request our director, Professor Chenglur, to please present a bouquet and a small memento to Professor Sen on our behalf. Sorry. So, friends, it's a great privilege and honor for me to introduce our speaker. As I said, Professor Sen is really one of the world's most outstanding theoretical physicists. He got his undergraduate education in Presidency College in Kolkata, got his master's degree from IIT Kanpur. How can I not mention that, my alma mater? His PhD from Stony Brook in the United States, the State University of New York at Stony Brook. And after that, after doing postdoctoral fellowships at Fermi National Accelerator Laboratory and the Stanford Linear Accelerator Collider, SLAC, he joined TIFR here in Mumbai in 1988. And I'm very proud to say, did some of his really very influential work here in Mumbai. Then in 1995, he moved to the Harish Chandra Research Institute in Allahabad and was there for several years till 2021, when he moved to the International Center for Theoretical Sciences, ICTS, in Bangalore, which, as some of you know, is also a center of TIFR. So in a sense, it was very nice to welcome him back to TIFR in 2021. Now, Professor Sen is really known for his wide-ranging and remarkable contributions in the area of string theory, and that is what he will tell us about today. So we're all looking forward to his talk. But let me say that in particular, one of the things he's very well known for is to show that, in fact, string theory has many different limits, or we can say manifestations, part of perhaps the title of his talk, but many different limits. People had earlier thought these were different kinds of theories, but he showed, in fact, that they're really different limits, different corners of the same underlying theory, the same underlying theoretical framework. And this has been a remarkably important idea in string theory, but also has implications in many other branches of physics and even mathematics. And so it's one of these really landmark, intellectually hugely impactful contributions that he has made. There are many others, but I thought I would at least mention this one. He is a winner of basically all the awards you can think of, but I'll just mention a few. He was awarded the Bhatnagar Award, the Infosys Prize, the World Academy of Sciences Prize, the Dirac Medal, and the Breakthrough Prize, which, as some of you know, is regarded as perhaps the greatest honor in the world for contributions to theoretical sciences. He's a member of various academies, the Indian Academy of Science, the Indian National Science Academy, and also the Royal Society. And I have to mention that he has been awarded both the Padma Shri and the Padma Bhushan by the Government of India for his outstanding contributions to science. So it's a really great honor to have him with us. But I want to end with a slightly personal comment, because it's been a great privilege for me to know Ashok for many years now. And you know what makes him so remarkable is he's a very simple person, if I may say, and that's itself an inspiration. He embodies this ideal we have of in India of a person who, lives a life of high thinking but simple living. And that's always been something that I've looked up to him for. But at the same time, he's been a great inspiration for people, say, of my generation, because, in a sense, the challenge we have had in TIFR is to show the world that we can do science at the highest of levels while continuing to remain in our core Indian. And this, I think, perhaps the best example of that I can say to you all, in my mind, is Ashok. And, one simple example is if you ever eat dinners with him, he eats with his hand. And I love that fact, and I do that too. And so he exemplifies this spirit that we can go all the way to the very top while continuing to be in our deep heart's core who we are. And for that reason, he's been a great inspiration to all of us in TIFR, in the string community, but also more generally across the country. So it's a great pleasure to have you with us, and we look forward to your talk today, which is entitled, I think, roughly String Theory and Its Many Manifestations. Thank you.
Okay, first of all, I would like to thank Sandeep for the kind introduction, and also for everybody for the invitation to come and speak here. It's really a great honor for me to be back in TIFR after some time. So today my talk is going to be on string theory. Now, string theory is a subject that has different appeals to different people. So what I am going to describe today is what the appeal of string theory is to me. Okay. And that essentially is the fact that string theory is an attempt to answer the question, what are the basic constituents of matter and what are their properties? So this, let me begin by giving a brief overview of the model understanding of the building blocks of matter. Okay. So at the crudest level, the building blocks are the molecules. But we know that molecules are not indivisible. Each molecule typically is made of several atoms. Atoms themselves are made of a central nucleus and a cloud of electrons. The nucleus, furthermore, is made of even smaller constituents called protons and neutrons. And the protons and neutrons themselves are made of even smaller constituents, which we call quarks and gluons. And furthermore, once one probes deeper into the structure of matter, one finds that quarks, gluons, and electrons, okay, as far as I know today, they are indivisible. Okay. But they are not the only elementary particles that we have in nature. They are in fact part of a big zoo of elementary particles. Okay. And later on, we'll get a glimpse of this zoo. Now, these elementary particles interact, okay, and that's what makes them interesting and non-trivial. They interact via various kinds of forces. Okay. And the four major forces that we know in nature are gravitational, electromagnetic, strong and weak. Okay. Gravitational and electromagnetic are familiar from day-to-day life. Okay. Gravity is what binds us to the earth. Electromagnetic waves in particular represent photons or carriers of light. Okay. But at the subatomic level, we also need strong and weak interactions to explain various properties of matter. For example, strong interaction is responsible for binding the protons and neutrons inside the nucleus, and the quarks and gluons inside protons and neutrons. And weak interaction, by its very name, is weak, but nevertheless, it's needed to explain various phenomena that we observe. For example, particular kinds of radioactive decays are caused by weak interactions. So these forces give rise to complicated interaction between elementary particles, and we measure these interactions by studying how the elementary particles scatter off each other. Okay. So typical experiment involving elementary particles involve throwing a pair of particles towards each other, okay, and then see what comes out. And then based on the observation of what comes out, we can reconstruct what kind of forces are at play between the elementary particles. Now it turns out that the effect of gravitational force between elementary particles is negligible compared to other forces. And this in fact can be done by a simple-minded calculation. We just have to compare the electrostatic force between two protons with the gravitational force between two protons at rest. So here is the simple formula. Okay, so the gravitational force between two protons at rest is given by Newton's law of gravity, which is given here. Here G is the Newton's gravitational constant, mp is the mass of the proton. It comes with a square because we are considering interaction between two protons. Okay. And r is the distance between the two protons. Okay, this is what we learned about Newton's law of gravity in high school. On the other hand, electrostatic force between two protons is given by a similar formula, the Coulomb's law, okay, which involves the square of the electric charge of the proton divided by the square of the distance. Okay. And we see from here that because both are inverse square law, the distance cancels out, and we are left with ratios that involves known constants. So the values of known constants I have given here. And if you plug in the values of these constants, we find that this ratio is an extremely tiny number, 10 to the minus 36. Okay. So this basically means that there is no hope that we can detect gravitational force between elementary particles in normal particle physics experiments, because it will be overwhelmed by the other kinds of forces. And we can make similar comparison between gravitational force and other forces. And one finds that all other forces are also much larger than the gravitational force at the level of elementary particles. Nevertheless, we know that the elementary particles must have gravitational force between them, because after all, the Earth and Sun, which are both made of elementary particles, do gravitate. So the goal of the theorist is to develop a theory of these elementary particles, a mathematical structure that will tell you, that will explain all the results of all experimental observations involving the elementary particles, but also predict results of new experiments that one could go ahead and try to verify by performing those experiments. But while developing such a theory, we should keep in mind two important points. The first point is that in typical experiments, elementary particles move very fast, and this means that we cannot use our standard classical Newton's laws that we learned in high school for studying elementary particles. We need to use special theory of relativity. The second observation is that the elementary particles are very small. So again, we cannot use classical laws. We need to describe them using the laws of quantum mechanics, because quantum mechanics is the theory that comes into play when you are dealing with particles which are very, very small. It turns out that we are lucky to have such a theory. We do have a theory that explains the properties of elementary particles, and this theory has been so successful that it has come to be known as the Standard Model, and it was developed through the work of many people, okay, over here. And so this theory is based on the principles of quantum mechanics and special theory of relativity. And in principle, this theory can be used to calculate the result of any experiment that we wish to perform involving elementary particles. So far, the Standard Model has been extremely successful in explaining almost all observed experimental data. People have tried very hard to find evidence that there is something beyond the Standard Model, okay, but most such attempts have failed, and people find that you do a lot of experiments with high precision, and at the end everything seems to match with that of a Standard Model. There are some exceptions that I am going to discuss in a few minutes. There is, however, one flaw in the Standard Model, and that is that it does not include gravity. So here is the list of elementary particles according to the Standard Model, and this is what I earlier referred to as the zoo of elementary particles. So the elementary particles according to the Standard Model can be divided into several classes. So the first class is what I have called quarks. These we encountered already earlier as constituents of protons and neutrons, and you see from this list that there are 6 varieties of quarks which are called up, down, charm, strange, top and bottom, and each of those come in fact in 3 varieties, okay, which are called colors. Okay, so each of these quarks, up quark comes in 3 forms, down quark comes in 3 forms, and so on. And at this point I can also add that protons and neutrons consist mostly of up and down quarks, but these quarks you discover when you collide particles at high energy, you produce these additional quarks. The second class of elementary particles are what are called leptons. Here you see our familiar electron that we encountered earlier as constituents of atom, but with electron comes its partner, okay, which is a neutral particle which we call neutrino. Okay, in particular the partner of the electron is what is called the electron neutrino. But besides the electron and the electron neutrino, there are heavier versions. Okay, so mu is a new particle which has properties similar to that of an electron, but it's just heavier, and similarly tau is also has properties similar to that of an electron, but it's even heavier than muon. Okay, and each of these come with their own partners, the muon neutrino and the tau neutrino. Then we have a set of particles which you can call mediators. These are the particles which are responsible for the various interactions or the forces that we describe between elementary particles. There are 8 gluons, okay, which are responsible for mediating strong interaction. There is a photon which is responsible for mediating electromagnetic forces. And then there are these 3 particles, W bosons and Z boson. These are responsible for mediating weak interactions. And we see that in this list there is no particle which mediates gravitational force, and that shows that Standard Model does not include gravity. And finally, there is a single particle called the Higgs. This particle in fact is, in some sense, is central to the Standard Model. Okay, this holds the theory together. This particle is responsible for explaining why the weak interaction is weak. Okay, and that it ensures that by making these particles massive. This particle is also responsible for the mass of the electron, muon, tau neutron, tau particle, as well as the quarks. And all of these particles have been observed by now. Even though when the standard model was first proposed, not all of these particles had been detected. Okay, so you can say standard model predicted the existence of certain particles, and then experimentalists went ahead and found those particles. The last example of such particle is the Higgs, which was discovered only in 2012. Now, as I said, despite its success, the standard model cannot be the final story. The first reason is somewhat mundane, that there are some experimental results which do not agree with the predictions of the standard model. And one example of such an experimental result is the mass of the neutrino. According to the standard model, neutrinos have no mass, but experiments found that neutrinos do have small but small but non-zero mass. So this means that standard model by itself cannot be the full story, but discrepancy of this kind can be easily explained by a minor modification of the standard model without giving up any of the basic principles. In particular, we can still maintain the principles of special relativity and quantum mechanics, and then just tweak the theory a little bit, and you can explain how neutrinos can have mass. But a more serious reason why standard model is not complete is that it does not contain one important force that we observe in nature, namely the gravitational force. Now, as we discussed, in all present experiments, gravitational force between elementary particles is extremely small and beyond measurement, but any complete theory must account for all forces, however small they may be. Because we certainly do know that even though we cannot directly measure gravitational force between elementary particles, gravitational force is present among elementary particles, because otherwise you wouldn't be able to explain why Earth and Sun gravitate. So then the question that arises naturally is it possible to modify the standard model so as to include gravity? So for this, let's recall that the standard model is based on the principles of special theory of relativity and quantum mechanics, and the framework that combines these two is also called quantum field theory. Okay, but you don't need to worry about the name at this stage. Okay, it's just enough to know that these are the principles that lie behind the standard model. So in order to combine gravity with the standard model, we need to first make the theory of gravity consistent with these principles. Then we have some hope that we can now put together gravity and the standard model and build a complete theory. The first step, which is to make gravity consistent with special theory of relativity, this was carried out by Einstein in 1915, and this is what we call the general theory of relativity. But the second step, which is to modify the general theory of relativity so that it becomes consistent with the principles of quantum mechanics, this turns out to be an extremely difficult problem. And attempts to make this consistent with quantum mechanics, the usual attempts have all failed. String theory comes in at this stage by providing a possible way out of this problem. And as we will see, it also provides a possible way of combining a theory of gravity with the theory of elementary particles. So let me then describe the basic idea of string theory. And the basic idea, in fact, is quite simple. It simply says that different elementary particles are just different vibrational states of a string. So instead of thinking the elementary constituents as point-like objects, we think of elementary constituents as string-like objects which are vibrating. And it can come in two varieties, one which are called closed strings which have no ends, and these are the open strings which have ends. Now the first question that one would ask is that if this is so, then why haven't we seen this? Okay, in all experiments we think of electron as a particle, we think of the quarks as particles. If they are really vibrational states of the string, we should have seen this. Now, the answer to this is contained within string theory itself, because one finds that the typical size of a string, in fact, is extremely tiny. It's of the order of 10 to the minus 33 centimeter. And this scale is much smaller than the length scale that can be proved by any present experiment, which in fact is of the order of 10 to the minus 17 centimeter. So it's not surprising that to a present experimentalist, the states of the string will appear to be particle-like objects. So we want to formulate a theory of strings, and this should be consistent with the principles of quantum mechanics and special theory of relativity, because these, as you saw, are two sacred principles based on which we formulate the standard model of particle physics. And the surprise is that as a consequence of these two requirements, strings automatically exert gravitational force on each other. More specifically, what one finds is that one of the states of the string actually mediate gravitational force. Okay, we said that strings can exist in different vibrational states. We find that one particular vibrational state of the string has exactly the right properties that a mediator of gravitational force will have, just like the gluons mediate strong interaction, the photons mediate electromagnetic interaction, and W plus, W minus, and Z mediate weak interaction. Okay. One of the states of the string will mediate gravitational interaction. Furthermore, the theory is automatically consistent with the principles of quantum mechanics and general theory of relativity. So in a sense, in string theory, gravity and quantum mechanics comes for free. Okay, that we just demand quantum mechanics and special relativity, and gravity pops out. Okay. Whereas, as I said, in the usual approach to formulating theory of point particles, okay, it's extremely hard to combine gravity with quantum mechanics. The price that we pay, however, is that string theory is very, very tightly constrained. It's so tightly constrained that we cannot adjust it to suit our needs. So in particular, we cannot demand that the dimension of space is what we observe in nature. Now, all of us are familiar with the fact that we live in 3 dimensions. Sometimes we call it 3 plus 1 dimension by adding the time. We also cannot demand that the different vibrational states of the string behave like the elementary particles we observe in nature. Okay. Although we would like to have this, right? One of the vibrational states of the string should describe the electron, another one should describe the muon, and so on. Okay. But this is not something that we can demand. We just have to take what string theory gives us. So one finds, first of all, by doing this analysis carefully, that there are 5 fully consistent string theories. And when I say fully consistent string theories, I mean that they are mathematically consistent, that if you want to compute the result of some process, then it better be that different ways of doing the computation gives the same answer every time. Okay, that's the meaning of mathematical consistency. And once you demand that, we find there are only 5 different ways you can formulate string theory. And these 5 different theories differ from each other in the way the string vibrates. Furthermore, one finds that in each of these 5 string theories, the dimension of space is 9, which is a little hard to imagine, right? How can a space be 9-dimensional? The way we describe 9-dimensional space is not by visualizing it, but by using the usual idea of coordinate geometry. Just like in describing a 3-dimensional space, we have to specify 3 coordinates. We abstractly think of a 9-dimensional space as a space which requires 9 coordinates to specify a point. So there is no difficulty mathematically in defining a 9-dimensional space. The only problem is that it doesn't describe what we see in nature. This, however, is not the end of the story, because one can show that this intrinsically 9-dimensional theory can be made to appear as if we have a 3-dimensional theory by using, in fact, a very old idea known as compactification. This goes back to almost the days of Einstein. Okay, it was developed by Kaluza and Klein, which can be a mechanism that can be used to make a higher dimensional space look lower dimension. And I'll try to explain this idea in the context of an imaginary world which has only 2 dimensions. Okay, and then we can generalize it to 9 dimensions. So for this, let's consider a 2-dimensional world with 2-dimensional people living on it. But we'll take the 2 space coordinates to describe the surface of an infinitely long cylinder of radius r instead of an infinite plane. And here it's important that you consider the surface of a cylinder. So don't worry about the interior. Okay, the interior in fact doesn't exist in this picture. Okay, the surface is the important thing. Okay, so everything moves on the surface, even light moves on the surface. So if you stay here and shine a light in this direction, it will come back and reach you after traveling a distance of 2 pi r. So if we are living in such a space, if you are 2-dimensional creatures living in such a space, then we see that if r is very, very large, say r is larger than the range of the most powerful telescopes that these 2-dimensional creatures might have, then the 2-dimensional space will appear to be infinite in both directions. Okay, so it will be indistinguishable from a regular 2-dimensional space which is flat and infinite in both directions. However, if r is not so large, then the space will be a little strange. Okay. Imagine that 2 pi r is about 100 meters. Okay. This means that standing in one place, you will see your image every 100 meters, right? Because the light will travel around and reach you. Okay, so if you look in this direction, you will see that there is an image of you 100 meters away. But we can consider also the opposite limit, where r is very, very small. As r becomes smaller and smaller, the world starts looking more and more one-dimensional. In particular, if r is smaller than the resolution of the most powerful microscope that these creatures might have, then for them the world will appear to be one-dimensional instead of being 2-dimensional. So we see that even though the space is intrinsically 2-dimensional, if the space is compact with a very small size, it can appear to be a 1-dimensional world. And the same idea in fact works in making a 9-dimensional space look 3-dimensional. We just have to take 6 of the 9 space directions to be small, describing some compact space K, and when the size of this compact space is sufficiently small, then the space will appear to be 3-dimensional. Now, we cannot choose any compact space. Mathematical consistency puts strong constraint on what kind of spaces we can use for compactification. Nevertheless, there are many different spaces K which can be used for compactification. And because of this choice, we see that even if we begin with a specific string theory, upon compactification, there are more possibilities. And these different possibilities may be regarded as different phases of the underlying string theory. And here by phases, I simply mean phases of matter, just like ice, water and steam are different phases of H2O. Okay, I'll have more to say about this analogy in a few slides. Okay, so here is the analogy again, that we know that a single theory that describes the H2O molecules and the force between them has different phases in the form of ice, water and steam. It's in this spirit, okay, just like the theory of H2O molecules can exist in these 3 phases. We can say a string theory has many phases which are characterized by many different choices of this compact space K. And just as the environment inside ice, water and steam are very different, similarly the 3-dimensional environment for different choices of the compact space K will be very different. Indeed, even the fundamental constants of nature, like the number of elementary particles or their masses and charges, will appear to be different in different phases. Now, it turns out that for some choices of K, the three-dimensional environment is very similar to the nature that we observe. In particular, this three-dimensional environment has elementary particles and forces similar to what we observe in nature, okay, like quarks and electrons and gluons and photons and so on. And this gives us hope that besides solving the problem of formulating a quantum theory of gravity, which of course each one of those phases solve, right? Each one of those phases have gravity built in. String theory also offers the possibility of combining this with a theory of elementary particles and their forces. The main challenge, however, is to find a phase of string theory that has exactly the elementary particles that you observe in nature, and this remains an open problem to this day. Okay, so you don't have a phase that it's not enough to say that we have phases which have properties similar to the elementary particles that you observe. We really need to find a phase that has exactly the properties of elementary particles that you observe. That should have the correct mass of the electron, correct mass of the muon, correct charge of the electron, and so on. So this is still a challenge. Now, here I want to push this analogy a little further. The analogy between different phases of string theory and different phases of H2O, in fact, goes further. So for this, let's suppose that you are living inside water and you wanted to study the properties of ice. We can do it easily because all you have to do is to freeze a part of water into ice and then do our experiments on ice. And we can do similar manipulations also with the phases of string theory. So here I have given an example. So let's suppose that we are living in a phase in which 6 of the 9 dimensions are circles of small size. Okay, this is a very simple kind of compactification. We just wrap 6 of the 9 dimensions into circles of small size, and so this will appear to be a 3-dimensional world like ours, because we cannot see any of the extra 6 dimensions. Living in this world, we can ask, is it possible to study properties of the phase in which all 9 dimensions are large? Right? Maybe all 9 dimensions are so large that we really think that we are living in 9-dimensional space. It turns out that we can. We can by creating a large black hole that carries appropriate charges in this 3-dimensional world. By creating such a large black hole, we can ensure that near the black hole, the space will open up into a 9-dimensional space. Instruments and study the properties of the 9-dimensional phase of the theory. We could in fact even go and live there and experience the 9-dimensional world, okay, near a black hole. And this is exactly like creating ice inside water. So here I have represented this pictorially. So far away from the black hole, you have 3-dimensional space. Okay, all the extra 6 dimensions are curled up into small size. As you approach the black hole, the size of these extra dimensions start increasing slowly. And near, very close to the black hole, the size becomes so large that it becomes indistinguishable from actually a 9-dimensional space. So you could send our instruments from there near the black hole, do our experiment and study properties of the 9-dimensional space. Or if we are adventurous enough, we can even go and live there. In fact, we can live also in the intermediate regions where the space is still curled up, but maybe it's curled up with a circumference of 100 meters. In which case, in that region, if you look in one of these 6 dimensions, you will find that you will find an image of yourself every 100 meters. So you could experience all these by creating an appropriate large black hole. So this, in a sense, is the ultimate luxury in space travel, where you create your own designer space-time and go and live there. So from what we have described so far, it would seem that there are altogether 5 consistent string theories, and each of these string theories have many different phases. And indeed, this was our understanding of the subject in the early days. But subsequent research showed that the 5 different string theories are not really different, but they all give different descriptions of the same underlying theory. And this unified underlying theory is in fact what we now call string theory. So you can describe this again by drawing an analogy. We can regard different phases of this unified string theory as some different points inside a room with 5 windows. Okay, imagine that you have a room with 5 windows. There are different points in the room which represent different phases of this underlying unified string theory. And these 5 windows are what we called 5 different string theories in the early days. And the point is that through each window, we see only a small part of the room. Okay, this technically this is called the weak coupling expansion. We have a small coupling. We can study this theory for small values of some parameters in a Taylor series expansion, and the Taylor series expansion is around the window, and you can go only so far with Taylor series expansion, and it starts breaking down once you start going deeper into the room. So if there is no overlap between the different parts that we can see through different windows, then we would not know that we are looking into the same room. And this is what describes the situation in the early days of string theory. But once we begin seeing deep enough into the room through each window, then we may get glimpse of some objects through more than one window. And then we realize that all the windows in fact open into the same room. And this is what describes the situation now. So we can see deep enough through each of those windows so that we recognize that we are in fact looking into the same room. Even though we get different views, different parts of the room are better seen from different windows, but we do know that we are looking into the same room. Now, one of the main directions of research in string theory involves attempts to open up new windows into this room. The most famous example of such a window is what is called the ADS-CFT correspondence, which says that some phases of string theory may be described by quantum theories of point particles or quantum field theory. Another example of such a window is called M theory. This is a particular phase of string theory which can be described by a theory living in 10 space dimensions instead of 9 space dimensions, even though each of the windows is based on a theory with 9 space dimensions. And all these phases can be created in the vicinity of appropriate black holes in the 3-dimensional phase of string theory that we described. Okay, so if we go back to this picture over here, that by choosing the charge of the black hole appropriately, we can create the ADS spaces, okay, which correspond to the window which has a dual, which has a description as a theory of point particles, or we can get to M theory, which corresponds to a 10-dimensional space instead of a 9-dimensional space. All you have to do is to adjust the charge of the black hole appropriately. So to summarize, the problem of connecting string theory to nature reduces to first demonstrating that there is a phase of string theory that describes exactly the nature that you observe, okay, which has the right masses and charges of elementary particles and the various other forces. And we also need to explain why nature exists in this particular phase and not in any other phase. And both these issues are currently under active investigation by many researchers. So I'll describe now a speculative solution of the second issue. Okay, let me remind you what the second issue was, that to explain why nature exists in a particular phase and not in any other phase, because string theory, as we learned, has many phases. So according to this speculation, no single phase of string theory is spatial. Different parts of the universe exist in different phases, and we see a particular phase of string theory because we happen to live in a particular region. This in fact is similar in spirit to the mechanism we described to create 9-dimensional space in a 3-dimensional world. Right? We saw that by placing a black hole, we can create regions where the phase is different from what the phase is at far away from the black hole. The difference, however, is that for the type of phase that we need to describe the universe around us, the actual mechanism is a bit more complicated than just having charged black holes. And this is based on the observation that many phases of string theory have the property that they expand rapidly, and this rapid expansion just follows the laws of general theory of relativity. So if we have such a rapidly expanding space-time, then once in a while bubbles of new phases can form in different regions via what is called a quantum phase transition. That we have some underlying phase which is rapidly expanding, and by spontaneous quantum fluctuation, different phases form in different parts of this rapidly expanding universe. Now, once these phases form, the bubble walls start expanding, but the rapid expansion of the medium separates them fast enough so that different bubbles do not collide. Okay, so they get separated quickly, preventing collision between them. So even though the bubble walls are expanding fast, the expansion of the intermediate medium is fast enough so that the walls don't collide. And this process in principle can continue for infinite time. So it is possible that every phase of string theory will be realized in some region of the universe. And if this picture is correct, then you see that no phase of string theory gets a spatial role in the universe as a whole, although in any given region, one phase will appear to be spatial. Okay, for example, if you are living inside this, then phase 1 will certainly appear to be spatial because phase 1 will describe the world around you. Okay. But if you are living here, then it's a phase 2 which will appear to be spatial. So this finishes the main story of string theory. But like many great epics, string theory also has many side stories. And these side stories involve possible application of string theory to solve problems in related fields. Each of these will constitute a lecture by itself, so I am not going to attempt to describe any of these, but I have just listed some of these side stories. Understanding black holes in quantum theory. Right? Because string theory is a theory of quantum gravity, it can be used to study properties of black holes in quantum theory. Okay, and much progress has been made in understanding black holes this way. The second aspect is string theory approach to solving problems in quantum field theory, which is a theory of point particles. But as we described, there are phases of string theory where there is a equivalent description as a theory of point particles. So using those phases, we can use string theory to study theories of point particles. Okay, again, a lot of progress has been made based on this approach. And string theory applications to mathematics. Here, the applications essentially come by computing things in different ways and verifying that they give the same answer. So let me go back to this picture here. So the way these mathematical identities, most of the applications of string theory to mathematics that have been made, come from the following analysis. Then you identify some particular phase of string theory that can be studied from 2 or more windows. Then you look at some quantity, something that you can observe in experiment, and compute that quantity both from this theory and that theory. From whichever theory you can observe it, you use that theory to compute it. You get 2 expressions, okay, one from each theory, and then the question will be, are those 2 expressions the same or not? Also, one finds that these 2 expressions don't look the same. But if they are not the same, then the whole idea of string theory falls through. So they better be the same. Otherwise, you have to declare string theory to be inconsistent. And in every case that has been analyzed, you do find that the results are the same. And often these results are the same as a result of new mathematical identities that people find based on this kind of analysis. Okay, many of these identities that one finds in string theory this way are something that was not known to the mathematicians earlier, but which were discovered only because string theory predicted some unusual relations between apparently two unrelated quantities. So all these make string theory a rich subject to study and explore. As I said, each of these can take one lecture or more. Okay, so I'll not try to explain any of these in any more detail. So now I'll just summarize the talk. So what I've tried to explain is that string theory is an attempt to formulate a theory of nature that would explain the existence and various properties of all the elementary particles and their forces. It's based on the idea that different elementary particles are different vibrational states of a string. String theory provides us with a consistent quantum theory of gravity and possibly of other forces. This is where, in fact, the main challenge lies. We also saw that initially it was thought that we have 5 consistent string theories, each existing in many different phases. But we now know that they describe different phases of the same theory. However, the main challenge remains, and that is to find the phase of unified string theory that describes the world around us. And we hope that this problem eventually will be addressed by someone. Thank you.
Okay, thank you so much, Ashok. We have time for some questions. Somebody's coming with the mic.
Thanks for a very great talk. So I'm an astrophysicist, so the formulation of the question may not be quite correct. So I was wondering this expanding phase where these other phase bubbles are getting created. So these new phase bubbles are also expanding.
Yes.
And will there other phase bubbles get created inside these?
Yes, indeed, that can happen.
And
yes.
is it always guaranteed by the theory that none of these bubbles will ever collide in each of these?
No, that may not happen, because sometimes it can happen that, see, these bubbles are formed by quantum fluctuations. Right? So if two bubbles form too close to each other, they may collide. Right? And then the phase which is dominant will win over. Right? The one which has a lower energy density, that will basically dominate. Right? So it can certainly happen that once in a while they will collide. Right? But statistically, there will always be different parts of the universe where different bubbles have formed.
But in principle, so when they collide, will there ever be a situation where you live with two phases in the same universe?
Well, that is only temporary, because it's like if you bring ice and water together, right? Then in thermal equilibrium, either water will freeze into ice or ice will melt into water, depending on the temperature, right? So here also it's like that. The one that has lower energy will basically win.
Okay. And another quick question. So this expanding phase, is it kind of similar to the expanding universe or completely different?
So this is basically the de Sitter phase, right? This is like a de Sitter universe. There is a non-zero cosmological constant in these phases, and that's what drives this expansion.
Thank you.
More questions?
Yeah, sort of an extension to the question there. So is it similar to eternal inflation concept of?
Yeah, it is similar to eternal inflation.
Right.
That's right.
My question may not be very technical. I'm a layman. What first motivated conceptualizing elementary particle as vibrations of strings? What gave the first clue, or what inspired that?
Yeah, okay.
idea?
I mean, the point of the discovery of string theory has somewhat checkered history, that it was not designed to give a theory of elementary particles. People are trying to explain strong interaction based on string theory. And essentially, okay, I mean, it's even there string theory was not there to begin with. People are trying to explain some properties of strong interactions. Somebody, Veneziano, wrote down a formula for what kind of formula we need for explaining those properties. And then people found that string theory actually reproduces that formula. But later on, we knew that string theory is not the correct description of strong interactions, at least not the string theory in the way I have described. Okay? Because there are other better versions, better theories which describe strong interaction. Okay? So string theory became dormant for a while. Okay? Till even sometime later, people found that string theory has these gravitational particles, the mediator of gravitational force. Okay? And that's where it started being described as a fundamental theory of elementary particles. Right? So it was not, because it will be very hard to imagine that you suddenly imagine that elementary particles are strings, right, without any motivation. So it was discovered accidentally, right? But then it was applied to the theory of elementary particles because it has naturally built-in mediator of gravitational force.
Thank you.
Excuse me?
Yes.
I'm referring to the dark energy spectroscope instrument results, which have not been peer reviewed, I know.
Yes.
But they're being talked about as an observational kind of, evidence of string theory, especially because of the part where they're talking about space-time things are not commutative.
Well, I don't
Is
think
that
that
right?
DAISY
You
results are
feel?
really, I mean, I wouldn't claim that DAISY results are either for or against string theory, right? One has to understand string theory, of course, has a possibility of such rolling scalars. Right? There are many scalar fields which can roll and which can produce varying cosmological constant of the kind that dark DAISY has found. But at this stage, I wouldn't say that it's a verification of string theory.
Kind of media-centric premature.
Yeah, no, I will not
thought as much.
I will not say that. Yeah.
Nishita.
Yeah, I just wanted to ask, you gave this example of making a black hole with the right charges, and then if you make an experiment near it, you should be able to see the extra dimensions. How
Yes.
would one even go about making such a black hole? What would that involve?
See, in our world, I don't know how to do it because in our world is different from this simple wrapped, simple compactification where each direction is just a circle. Okay. But imagine that you are living in such a world, right? This 3 plus the 3-dimensional world where 6 of the dimensions each are compact. Okay. So there, I mean, one way to go around making the black hole is the following: okay, that we first create some massive object, right? Take a planet, okay, or the sun or the black hole, and then you throw in these charged particles one by one. Okay, you know precisely what kind of charge the particle has to carry. Those are elementary particles. You keep throwing in the elementary particles one by one, so that the charge of the black hole builds up. Okay. And it has to build up so much that the total mass of the final black hole is dominated by the elementary particles that you have thrown in. Okay. So the initial mass was just so that the particles bind, okay, that they fall into that planet or star or whatever and binds gravitationally to the planet or star. So this way you build up the total mass, which is much larger than the initial mass that you started with. And that black hole will have this property, that close to the black hole, the space-time will look 9 plus 1 dimensional. But this is not our world, right? Our world is not as simple as when we just have the extra dimensions carved up into circles.
Questions?
The current understanding of string theory, how much will it be different if we go in an expanding space? For example, like light years away, when the space is expanding, there are scalar fields and gravitational and electromagnetic fields being expanded. So the core understanding and the calculation, will it be the same, or will it be affected by the expansion of space spontaneously away from, like, light years away from Earth?
The expansion of the universe?
Yeah.
You mean the expansion of the universe?
Yeah, how will it affect, like,
yeah, see, the expansion of the universe has to be built in the string theory itself, right? So when I said that you have to identify the correct phase of string theory, right, that correct phase will also have the property that it produces an expanding universe, right, like a dark energy, cosmological constant, or some rolling scalar field. So all of these are requirements of the correct phase of string theory.
So expanding of space is just another phase of string theory, like you spoke earlier, like.
Exactly,
Okay,
that's
cool,
right.
cool.
So our universe has to be in that expanding phase.
Thank you.
Thank you very much for a fantastic talk.
you.
So the take-home message is that you will need black holes to probe string theory, especially in the.
No, I don't think that is the take-home message, because this example that I gave with black holes, right, that is only for a very specific kind of compact space where each of the extra directions are wrapped in a circle.
Sure. So the extra,
Yeah, as far as you know, our universe is not like that, right? The kind of phase that we are living in, that may change in the future, right? We don't have a clear understanding of what kind of phase you are living in, right? As far as you know, the current phase of the universe is not of this kind, right? Where you have the simple compact circles. If it turns out that there is some simple compact circles, right, then indeed we can try to build such a system, okay, where you have black holes, and near the black hole, at least one or more of the dimensions will open up. But in our current understanding, our phase is not like that.
So I'm a bit confused there. I mean, suppose I have a way to probe very close to the black hole, for
Yes.
example, Event Horizon Telescope. So can, very clear prediction can be made for such observation. We may not have resolution right now. That's one possibility. The other one is that imagine a scenario that I can actually look for two binary, for example, black hole binaries, maybe for 10,000 years. I can tell you a way to do that. Will string theory can make these extra dimensions can actually change in the sense of you have scalar fields that can actually affect the dynamics, and in 10,000 years you can put very strong constraint. Is that possible?
Yeah. So okay. So let me explain this again. Right. So here you see what I have said. Suppose you are living in a phase in which 6 of the 9 dimensions are circles of small size. Okay. This is not needed, but at least one of the compact dimensions have to be. If one of the compact dimensions is a circle of small size, right? Circle is different from general space. Right? Then this mechanism works that you can build a black hole and open up that circle. If the compact space is more complicated, then what I described here is not true. Right? It may still be possible that there are other experiments which will open up extra dimensions. But the use of black holes to open up extra dimensions, what for a particular kind of compact space, particular kind of compactification. So if you are living in this kind of compact space, then indeed we can study black holes and we can see this extra dimension.
Yeah.
But that depends on what kind of phase you are living in.
Thank you. So, but in any compactified surfaces, it will be, the dimension, this will be, the distances will be circular.
No. See, that's the point. That
periodic, no.
Not even periodic, but it's, for example, Calabi-Yau manifolds have a very complicated structure. There can be fluxes through the Calabi-Yau manifolds, right, which makes things even more complicated. So what we need, if there are massless scalar fields or very light scalar fields, then you can use those scalar fields to open up extra dimension. We don't know if in our universe there are light scalar fields of that kind.
Yes, there are very strict constraints on scalar fields.
Yeah. So on the other hand, the Daisy result, which says that the cosmological constant is changing, right, suggests that maybe if the Daisy result stands, then presumably there is a light scalar field, right, which is responsible for change of cosmological constant, which we just haven't found for some reason.
If such scalar field exists, can they be sort of?
Yeah. So if such scalar field exists, then it is possible that by creating appropriate systems, we can make the scalar field expectation value different from what it is here.
Sure.
Right? And that is something we can observe.
So if such things happen, then naturally those scalar fields will be coming very close to, because of the strong gravity.
Yeah.
So the black holes will
very close to either black hole or some other system, wherever you can produce strong gravity or strong electromagnetic field, those scalar fields may take values that are different from what they are far away from the black hole.
Okay. Thank you. Thank you.
Maybe one last question there.
So since we know that string theory can explain the elementary particles included in the standard model, so does string theories predict something about gravitons if and when we discover it?
Yeah, so string theory of course has gravitons. In fact, that is one property of string theory that is common to all phases, right? That it always has a graviton. So that's a constant in string theory. Right? Other elementary particles are defined between different phases.
But different versions of string theory will give the same theory for graviton. It will be means coinciding to something common.
At long distances of the kind that you are familiar with in gravity, it will be the same theory. And then at short distances, there can be corrections, and those corrections may depend on different phases. Right? But at long distances, it will be the standard gravity that we are familiar with.
Thank you.
Okay, if there are no more, if there's another urgent question. Okay, there's an urgent question there.
Yeah, so I guess urgent question, but what I wanted to ask was like, do these phases in the phase bubbles, do they remain constant, or do they have a time evolution? And like, how exactly are we defining the boundaries of these phase bubbles?
Yeah, so the boundaries typically expand at the speed of light. From the point of view of the intervening medium, the boundaries of the phases of each of these phases expand at the speed of light. Right? But in the interior, they just remain in that phase, right? Till maybe another bubble forms by quantum fluctuation in the interior of this phase. Right? That can also happen. Right? That it's not that these phases can all remain forever. Right? Sometimes some other bubble can form inside this phase. But otherwise, till that happens, the interior of the phase remains in the same phase over time.
All right, thank you.
Okay, so let us thank Ashok for a fabulous talk. One last announcement. Those of you who are joining us for dinner, despite previous announcements, the dinner is not in the guest house. It is in the colonnade outside the West Canteen. Okay, so and of course, for everyone, there's hardly outside. Please join.